Hi, everyone. My name is Guy, and I'll be telling you about joint work with Moses Charikar on multi-way online correlated selection. The problem we consider in this work is that of edge-weighted online bipartite matching. And if you've never heard of it, don't worry. In this slide, I'm going to explain to you how it works. So I have a bipartite graph with two sets of vertices. The left vertices are offline, and so known ahead of time. The right vertices appear one at a time. So as an online vertex appears, all of the edges attached to it also appear. And at that time, we have to decide which of these edges to pick. And so let's say we pick this weight 3 edge. Only after we make that irrevocable decision does the next online node appear. And once it does, we once again receive all of its edges and again make a decision on a matching until the entire graph has been revealed. In this case, we might be a little bit sad because we would like to pick this weight 2 edge, but we already have an edge attached to the corresponding offline node. We'll actually allow ourselves to pick multiple edges attached to the same offline vertex. And when we do, we dispose of any previous edges and don't get any benefit from them. So in this case, our score wouldn't be 3 plus 1 plus 2 being 6. We would dispose of this weight 1 edge and so get a score of 5. Effectively, we take the max weight for each offline node. This is called the free disposal assumption. And one motivation for it is that you can't get any non-trivial competitive ratios without it. Also, in many applications, it's quite natural. There are different applications you can think of, but one is internet advertisements, where you can think of the online vertices being an impression, one person arriving to a web page with space for one ad. And then the offline nodes are advertisers that are bidding for each user. And so advertisers are okay with getting extra impressions of their ads, but might not be willing to pay extra for more than they asked for. And there are other applications where this a free disposal assumption makes sense as well. It is standard when considering this problem. When we analyze our algorithm, we compare the score we achieve to the optimal score with hindsight, if we knew the entire graph. In this case, you could pick all the horizontal edges and get an optimal score of 7. And then we can compute the competitive ratio, which is our score over the optimal score. And to achieve good competitive ratios on this task, we need randomized algorithms. And so we'll actually take the expected competitive ratio over the randomness of our algorithm as the numerator. Our goal will be to get competitive ratios that are as large as possible on worst case input graphs. This edge-weighted online bipartite matching really sits at the current frontier of what we know how to do and what we don't know how to do. So I've listed 4 problems here in increasing generality, ranging from the version of this problem where there are no weights on edges to a version of this problem where, roughly speaking, we replace that max with any submodular function. And people have studied these for many years. For this most general problem, the greedy algorithm has been known for a while to get a 1/2 competitive algorithm. More recently, we got an essentially matching upper bound saying that for efficient algorithms, it's very likely that 1/2 is the best possible. Work for this online matching problems was really sparked in 1990 by a seminal work with Karp, Bazarani, and Bazarani, which gave a 1 minus 1 over E competitive algorithm for the unweighted version of this problem. And they also gave a matching upper bound saying that no algorithm can do better than 1 minus 1 over E. And this upper bound is still the best known upper bound for both the vertex weighted and edge weighted version of the problem. More recently, for the vertex weighted version of the problem, a 1 minus 1 over E algorithm was given, completely closing the book on the vertex weighted version. But until a 1.5 years ago, the edge weighted version remained nebulous. We didn't know whether it was as hard as monotone to modular welfare maximization, and maybe 1/2 was the best we could do, or maybe it's as easy as the vertex weighted version of the problem, until a best paper at last year's FOCS by Farbach et al. Gave a 0.5086 competitive algorithm, thereby showing that this problem is easier than monotone to modular welfare maximization. In this work, we're going to give a 0.5368 competitive algorithm for the edge-weighted setting. And actually, concurrent work at the same FOCS gives a 0.519 competitive algorithm. All three works use somewhat similar techniques with something called online correlated selection, which I'll abbreviate OCS in coming slides. For time purposes, I'm not going to have time to give a comparison between ours and the concurrent work, but I encourage you to listen to their talk. Feel free to ask me or them questions or read the papers for a more in-depth comparison. I will try to give a brief comparison of how our OCS compares to the prior work of Farbach et al. But once again, for time purposes, it will be somewhat brief. Okay, so we're really building upon their techniques to get better competitive ratios and hopefully introduce objects that will be useful in a variety of problems. Okay, so our proof of this 0.5386 competitive ratio involves definitions of various objects. We have something called a continuous OCS, a discrete OCS, a strength distribution, and many reductions between each of them, showing how to get from all the way from strength distribution back up to an algorithm for edge-weighted online bipartite matching. For time purposes, I'm not going to have time to go into each of these definitions and their reductions. I'm really just going to focus on this first part of the diagram. I'll give you the definition of a continuous OCS at a high level and some intuition for why it might be useful for edge-weighted online bipartite matching. Okay, so let's dive into online correlated selection, OCS. So the key idea here, and this is true both in our work, the previous work, and the concurrent work, is to separate the algorithm into two components, a deterministic component and a randomized component. And actually, so the randomized component is the OCS, and we can actually think of the OCS as being blindfolded. It will not know the input instance. It will only know what the deterministic component tells it. So then, as we went over earlier in this problem, one by one, the online nodes appear. And when they do, the corresponding edges and their weights are revealed. The deterministic component gets to look at the revealed information, but it's fully deterministic, and we don't want to make deterministic choices in this algorithms. So the deterministic component instead decides on a distribution of choices to make at this iteration. It might say, oh, well, B has a high weight, so let's put a higher probability on selecting B than we do on A and C. And it tells the OCS this distribution. The OCS is allowed to be randomized, so it rolls its internal randomness and then picks an edge consistent with this distribution. So there should be a 30% probability that it will select C this round. And let's say C was a selection that occurs. Okay, and then this process continues. So in this next iteration, we have two edges appear. But something we're going to enforce is that the deterministic component will not know what edge was actually selected. It will only know the distribution it gave. And the reason for that is if it knew the edge that was selected and its function depended on it, well, the edge selected depends on randomness, and so the deterministic component would not be fully deterministic. So we actually hide that information. The deterministic component might think, oh, well, I put a high probability on B being selected in the previous iteration. So this iteration, I don't want to double match, and let me put a high probability on C being selected. And it doesn't know that in reality, C was the edge selected. So it passes this to the OCS. The OCS is forced to pick marginally by this distribution. So in this iteration, there must be a 70% probability of being C. But it's allowed to correlate its decisions across iterations. And indeed, that will be very important. And since it knows that it picked C in the previous iteration, ideal OCS will have a slightly less than 70% chance of picking C in this iteration, conditioned upon picking C in the previous iteration. Let's say that happens here, and the OCS saves the day. So instead of double matching C, we randomly select B. With different randomness, we could have selected C twice or had a different outcome. This is just one example. And now, very briefly, to contrast the definition, or not full definition, but kind of the interface I just gave for our OCS. The difference between this OCS and the one in the prior work from last year's FOCS is that in their work, the OCS only selects a pair of elements, and it puts 50% probability on each thing in the pair. It's not allowed to select arbitrary probabilities. One way to view it is it can either select a single element and have probability 100%, or two elements and a probability 50% on each. Those are the only things it can do. So there's a more limited interface in how the OCS, what the OCS can accept. We accept arbitrary probability distributions. They accept pairs of elements or a single element to match with probability 100%. And just for time purposes, that's kind of all I'll be able to go into in the difference of the two OCSs. Okay, so we've had this interface in how the two components communicate. And next up, we want to get some intuition for how we want the OCS, what sort of guarantees we want from the OCS in order to get a good competitive ratio. And recall that in order to maximize the competitive ratio, we want to maximize the expected score. So first, just using linearity of expectation, we're going to rewrite that expected score as a summation over the offline vertices of the maximum weight edge attached to each offline vertex. And once again, rewrite that using an integral as the integral from w equals 0 to infinity of the probability I being matched to a edge with weight at least w. That's a standard integral trick. And lastly, not much is happening here. We're just taking the complement of this event. But we get the integral of 1 minus the probability I is not matched to something with weight at least w. And the reason we do the complement of the event is our OCS will have guarantees about things like this. Our OCS will guarantee for each individual offline vertex and every weight level that this probability is somewhat small, depending on the input it has received. And as we make this probability smaller, we increase the expected score. So by upper bounding how large these probabilities can be, we lower bound the expected score and therefore lower bound the competitive ratio, which is what we want to do. Okay, so what sorts of guarantees can we make about this? Well, first, we're going to consider the OCS that at each iteration makes independent choices. So recall, it's given a distribution. It's going to select something consistent with that distribution. So, if it's told to pick something with probably 30%, it will pick it with probably 30%. And then this first OCS will forget what decisions it made in previous iterations. And for each new iteration, independently roll according to that distribution. This is just for intuition's sake. It's not actually good to have an OCS that makes independent choices. We want something better. But for now, let's just think about this OCS. So let's say this is the input graph. And there are multiple offline vertices here, but we're just going to isolate one offline vertex and look at the information the OCS has received about it. It doesn't actually know the weights, but the OCS has been told the first edge pick A with probability 0.2, then probability 0.5, then with 0.5, then with 0.3. So if we want to compute the probability that A is not matched to anything with weight 4 or more, that's the probability it's not matched to the red edges, the first, the third, and the fourth. And that is, in the case of independent choices, exactly equal to 0.8 times 0.5 times 0.7, which using an approximation is roughly e to the negative 1. So if the OCS makes independent choices, our guarantee will be of a form like this. Now, it's not too hard to show that if we make independent choices at each iteration, the best possible competitive ratio we can get is a half, which is only as good as the greedy algorithm and so not very useful. But later we'll see that if we have an OCS that does a little bit better than independent, we'll be able to get this competitive ratio above a half. Okay, so what does it mean to have an OCS that is better than independent? And to go over a full definition of how we quantify the strength of the OCS would require introducing more notation than I would like in this presentation. So instead, I'm going to do a definition by example and see what sorts of guarantee an OCS has. The definition of an F continuous OCS is parameterized by a function f, which you should think of f of x being something slightly smaller than e to the negative x. And the smaller f is, the stronger the OCS is. Just the word continuous is just in contrast to some other OCSs where the probabilities can't be any number, but they have to be discrete choices, similar to the definition of Farbach et al. So that's why we have continuous here, but that won't be important for the purpose of this presentation. Okay, so let's say we have an F continuous OCS. What guarantees does that lead to? So first, let's say we want to compute the probability A is not matched to either of the last two edges. In an F continuous OCS, what we do is we say, oh, these two edges were consecutive. They were two online nodes that appeared one after the other. And so to bound that weight, we take the function f of the sum of their probabilities, f of 0.8. In contrast, when the edges we're bounding are not consecutive, so in this case, we're bounding the probability the first, the third, or the fourth edge are not selected. We don't just sum up their probabilities. We don't get f of 0.1. We kind of treat them as pseudo-independent. We want our OCS to guarantee that the probability none of these three edges are selected is f of 0.8, which is the probability this group is not selected, times f of 0.2, which is the probability this one is not selected. And we need our OCS to smoothly interpolate between these two extremes. And it smoothly interpolates depending on how much probability mass is between them. So in this example, the probability between them is 0.5, which is somewhat large. So we kind of treat them as if they were effectively independent. But as that probability approaches 0, we want it to be almost as if they were consecutive. And so our OCS's guarantee should become more like f of 1, which for the f we consider will be quite a bit smaller than f of 0.2 times f of 0.8. So these are, if an object is an f continuous OCS, it should satisfy these guarantees. And I haven't told you how to construct it because of time, but a large portion of our paper is constructing objects that meet these guarantees. Now, going into the full formality of this interpolation and how we parameterize the guarantee we should get would take some time, but really the most important thing to know is it just interpolates between the two extremes. Okay, so if we had an F continuous OCS, then we want to use it to build an algorithm for edge-weighted online bipartite matching. And we have a meta theorem showing how to do that. So for any F continuous OCS, we can use it to construct a gamma competitive algorithm for gamma given by this really concise formula, this integral. And as you might expect, as F goes down, which corresponds to stronger OCSs, the competitive ratio goes up. And just a quick contrast. So this formula in comparison to the prior work, they also had a way of going from their definition of an OCS to a competitive ratio, but it was through a linear program, which was used to compute various parameters and out popped a competitive ratio. In contrast with our definition of an OCS, we get a concise analytic formula, and we can actually use our techniques to also get a concise analytic formula for their definition. And so removing the need for their linear program to pop out competitive ratio. Okay, so the proof of this theorem comes from the online primal dual framework, which is used for lots of online algorithms. It's used to design the deterministic component to take advantage of the OCS and analyzes the competitive ratio that they get written together. And once you have the right definition and you know the proof of Farbach et al.'s corresponding theorem, it's not super difficult to get this, but there is, a fair bit of like technical detail that we have to run through to derive this. And in particular, getting the definition right takes some time. So some intuition for this formula. We can first consider the fully independent OCS, which corresponds to an f of e to the negative x. And if we do this, as we might expect, we get a competitive ratio of 1/2, which isn't super useful. That's the same as greedy. But as we push down, we get better competitive ratios. And we can imagine what happens when we get something like a perfect negative correlation, which it's not too important what this is, but it's kind of an extreme you can imagine of how good an OCS can be. And you can actually show you can't do quite this well, but it's still a useful thought experiment. And at that extreme, we get a competitive ratio of 1 - 1 over e, matching upper bounds. As we do work in the middle, we get a competitive ratio in the middle. So anything we can do better than independent leads to a competitive ratio better than 1/2. And indeed, that's what we do. We show how to construct an OCS that's better than independent, and therefore get a competitive ratio greater than 1/2. Okay, so to conclude, just a reminder that this was only one part of our paper, and there's more to see if you're interested. So hopefully you have some intuition for how this continuous OCS definition works and why it might be useful. But if you're interested in how to construct them and the sorts of techniques that can be used, feel free to talk to me or read our paper. Okay, thank you for listening.